And before I start to speak about Bose-Einstein condensation of magnons, I would like to say a few words about what magnons are. So you probably know from solid state physics that the simplest model of a ferromagnet is the chain of spins which are parallel to each other. And this is a ground state of a ferromagnet. So, and this ground state corresponds to this to the angular momentum, maximal value of the angular momentum. And from the quantum mechanics, we know that excited states of such a chain, such a ferromagnet, have a quantized spins. So the first excited state will correspond to the spin, the maximum -1. The next will be maximum -2, and so on and so forth. In magnetics, in magnetic solid states, it calls that we create 1 magnon, 2 magnons, 3 magnons, and so on. So from this simple picture, it is already clear that magnons are Bose particle because each magnon carry on the spin equal to 1. What is more important? What is also important that if you think that 1 magnons correspond to the just rotation of 1 spin half, this is not true because such a state, localized perturbation, is not stable due to exchange interaction in ferromagnet. This rotated spin will try to rotate his neighbors. Their neighbors will start to rotate their neighbors, and so on and so forth. And instead of this structure, which corresponds to the excited states, one has delocalized excitation, where all spins are have a little bit smaller z component, but due to interaction to each other, they create a wave. So you can see here nicely how the wave propagates in that direction. So these are spin waves, and from quantum mechanical point of view, we can call the quanta of these spin waves magnets. It is a full analogy with phonons, with the sound. So if you have a lattice and you move one atom out of equilibrium, it cannot stay in this equilibrium. Instead, the entire lattice starts to vibrate, and there is a waves. And the spins of in magnetic system, the analog of phonons are magnons. For the specialists, especially theoreticians, I'd like to emphasize that important thing here that magnons carry transverse magnetization. So that it's not only a reduction of longitudinal magnetization, but since they are rotating, they carry on transverse magnetization. And what is Bose-Einstein condensation is that really ordering of transverse magnetization. But this is just notes for specialists. Now, let us think about what is Bose-Einstein condensation is. Again, consider a very simple case. Statistical physics, well, I think this is third semester. If you have a Boltzmann statistic, you have a classical gas, we have the Boltzmann distribution, number of particles with a given energy, call it Maxwell distribution, Boltzmann, whatever it is. And its distribution is described by this equation. Now, we take another gas, the same gas, or another gas with the same density. It's also described by this distribution. And now we increase the density by a factor of 2. So we put these two gases together. What happens? Well, nothing happens. The distribution will be the same. Distribution will be the same. The only things which happens, we will have larger total density. So normalization of this distribution will be increased. So the density of states will be increased. So we increase the chemical potential, strictly speaking. But since in this equation chemical potential gives you just prefactor, the dependence of the distribution function, the number, how many atoms possess a given energy, will be the same. So, and this has a very deep, very deep reason, because in a classical gas, we don't have a no lateral scale. We have no at a given temperature, there is no lateral scale with which we can compare the mean distance between molecules or between atoms. The situation is completely different for quantum statistics. Now we have, I'm talking about Bose statistics. The Bose statistics is described by this equation, and this -1 change the situation completely. There is just a constant. It's changed the situation completely, and again, we make the same game. We consider a gas, then we take another gas, the same density. They are described, the equation is, the distribution is described by this equation. And you look, if you now, before we make the game, you will see that in this equation there is a divergence. If, for example, in this equation energy is equal to chemical potential, we have exponential of 0 is 1, 1 minus 1 is 0, so we have a 0 here. It means that according to this equation, the population function at energy equal to chemical potential should diverge. But in most of situation, the chemical potential in gas is negative. And of course, there is no states with negative energies, because energy in gas starts with 0. Therefore, this divergence is just, it's not real, it's just imaginary divergence. But now, we put them together. And if we put them together, the density increase. And due to increased density, we again increase the chemical potential. But since now in this equation, chemical potential is not only defined as a prefactor, which just normalizes the entire function, we see that for this higher density, we have another distribution function. And this is the main difference between classical statistics and quantum statistics, that the distribution function, the shape of the distribution function, depends on the chemical potential and on the density. And again, this has something to do with, in quantum statistics, we have a intrinsic scale, and this intrinsic scale is de Broglie wavelengths. And now we can compare the de Broglie wavelengths at given temperature with the mean distance between atoms. And therefore, when we change the mean distance between the atoms, we can change the shape of the distribution. And again, we can ask ourselves the question, what happens if we increase the chemical potential further and further, and at some density, the chemical potential becomes 0, and we have the energy states at the energy equal to chemical potential. What happens? And the answer is given by Einstein in 1925. He calculated this, analyzed this problem theoretically, and he predicted that although that macroscopical part of the particles occupies the single state, which correspond to the energy which is equal to chemical potential, and build a coherent condensate. From this simple consideration, we understand that a big number of particles will be occupy the states, but from this simple consideration, we cannot say about any coherency, but the prediction of Einstein was that will be coherent condensate. And this is what people call Bose-Einstein condensation. And as I said, we can, the the most important, most prominent example of Bose-Einstein condensation is Bose-condensation of atom. If you have a classical gas, we have point atoms which are moving with a given velocity, and they have a well-defined position. In a quantum gas, we have de Broglie particles, well, wave packets, so they delocalized, but still we have some kind of partially localized quasi-particles. But in BAC, a part of the density of the gas is represented by uniform wave function, which fills uniformly the entire volume. And this is Bose-condensate. But on the top, of course, if the temperature is not zero, one has also non-condensed atoms. And the conditions of the Bose-Einstein condensation calculated by Einstein was rather simple. So the critical temperature is determined by just by density of the gas and its mass. And there's Planck constant. What I'd like to emphasize here, that in this equation, contrary to the superconductivity, we have no any energy scale. So critical temperature is just proportional to some power of the density. So in principle, the critical temperature can be as high as we want, even room temperature or even high. The only problem is to have dense enough gas. And we can calculate, put this equation in other form to say at any temperature we can have a transition if we have a critical density. And this is the most I think, surprising thing when people think about the Bose-Einstein condensation is very low, needs a very low temperature, but it's not intrinsic. It is just connected with the fact that for particular system, gas of atoms, you cannot reach high enough density because at much smaller density, instead of gas, you build a fluid or even solid state. So it's just, it's not intrinsic. And from the thermodynamics, the condition, this condition corresponds again to some rather simple conditions, and de Broglie wavelengths of a particle, which determined by the temperature, should be order of magnitude of the mean distance between the particles, which is proportional to the density in -1/3 power. Therefore, for energy, which is determined by the temperature, you have power 2/3. You can also analyze the same problem thermodynamically, as I suggested in the beginning, and the condition for this transition is very simple, that chemical potential should be equal to the minimum energy. And classical papers devoted to the gas, it is written that the chemical potential should be 0, because in gas, the minimum energy is 0. But we will see that in magnons, gas, it's not 0, because magnons have a gap in their spectrum, and therefore their energy is not, the minimum energy is not 0. And therefore the condition should be that the chemical potential should be equal to some non-zero value. Now, and this is what you see here, this is a picture from the Nobel Prize paper, where you see the people were investigating the distribution of atoms. Here you see the number of atoms having well-defined velocity or energy, and you see that before at some temperature the distribution is quite broad, and according to the statistics. But if you have some a given temperature, and on the top of this broad distribution, you have very narrow peak, which correspond coherent state. And if temperature is even less, you have a very narrow peak where almost all atoms correspond to the states with a group with a velocity and energy equal to 0. Now, come back to our magnons. What is important? Important, as I said, the energy of the magnons, because we are talking about distribution. And what is important is how the energy of magnons depends on their wave vector. We know very simple that for atoms, energy is proportional to the wave vector squared, just parabolic dispersion. For phonons, for example, energy is proportional to the k in the first sound with a constant speed of sound. In light, we have the same. In magnons, we have quite complex situation, and it has something to do with that in magnetic system, we have 3 types of interactions between atoms, between spins. And all these 3 types of interactions contribute to the dispersion law of magnons. These are Zeeman energy. So that means as soon as we have a magnetic field, all spins processing with a given frequency, Larmor frequency. And since this is one single atom energy, it does not depend on the k vector, does not depend on all spins processing in phase or out of phase, because each spin just interacts with magnetic field. Then there is exchange, and which is shown where the exchange interaction is proportional to the angle between neighboring spins, and therefore it is clear that if you have a wave with much shorter wavelengths, the angle between neighboring spin becomes larger and larger, and if you calculate that you have contribution which is proportional parabolic, contribution which is proportional to the k squared. And there is a dipole-dipole interaction, and this is long-range interaction. Therefore, it is very difficult for me to explain to you in few words why this contribution is very unusual. It has maximum at 0 wave vector and goes down at larger wave vector. The simplest things I can say, look, since it's long-range interaction, if we have large k vector, means small wavelengths, over the long range of the interaction, it will be averaged to 0, and therefore this dependence is such that it goes to 0 at large k vector. Therefore, if we add all these 3 contributions, we will get this red curve, which is rather unusual. And you see that you have a minimum energy, not in k equals 0, which is the case for waves we know, for atoms, for phonons, for photons. But in this case, this is the minimum energy corresponds to well-defined wave vectors, and it depends on the interaction between correspondence between dipole-dipole interaction and the exchange interaction. And this curve is calculated for specific material, yttrium, iron, garnet, for a film with a given density for well-defined magnetic field. And this is showing you how this k vector is defined. And you see that this, since the dipole-dipole interaction, again for theoretician, is anisotropic, its contribution is also anisotropic, and what I have shown here is for the direction k parallel to the field, and this is, and for k perpendicular to the field, contribution is much larger, and that is not important for us mainly because we are looking for the minimum energy, and that corresponds to the minimum energy. So that is the dispersion which we are mainly interested in, and as I said, this yttrium iron garnet is very good material. It's transparent. It's it's magnetic, and one can make films very easily. And again, the difference for people who are working in the field of atomic BEC notes that contrary to the atomic gases where the scattering amplitude is a constant, is a model of solid balls. In magnetic material, scattering amplitude for magnets depends on the wave vector. But it's just, yeah?
Yeah, sir. Presumably the fact that the spectrum doesn't go to zero at zero momentum is because you have magnetic field, right?
Not necessary.
Otherwise you still have the Goldstone theorem.
No.
Goldstone theorem doesn't care about long-range interactions, short-range interactions. As long as you have a continuous symmetry, you're guaranteed to have k omega going to zero.
Your statement is correct in the absence of anisotropy.
Oh, you have anisotropy.
I have no anisotropy in this particular case, but in general, it may be instead of magnetic field, you can have anisotropy. But you are right, in this particular case, this gap is determined by the magnetic field. And of course, if you have no anisotropy and you have no magnetic field, as you said, you have Goldstone mode, and the ground state is not stable, then we have domains. And therefore, since I don't want to have domains, I want to have as simple as possible ground state to investigate Manson, I have to apply magnetic field. So you are correct. But as I said, this dispersion is anisotropic. You will see two cuts. For k parallel to magnetic field, we have discussed it. For k perpendicular to the field, it's different, but we don't care. It's with higher frequency. What is important that we can see that it's more or less parabolic, and we can introduce effective mass, and this effective mass is order of magnitude of effective mass of free electron instead of atoms. And what is also important that in the formula of Einstein, mass is the critical temperature is inverse proportional to the mass. Therefore, since we have smaller mass in the atoms, at the same density, we should have higher temperature, critical temperature. But magnons are weakly interacting particles, and therefore we can reach density of magnons is many orders of magnitude larger than one can, and still have a gas of magnons than in a gas of atoms. And what is important, just to have a feeling that this gap, minimum frequency, if you calculate it, the minimum energy corresponds to the 100 millikelvin. Although these experiments were performed at room temperature, this tiny gap make a change. As we have heard from these comments, these tiny gaps stabilize as the ground states, and therefore, although it's much smaller than the temperature, it's still very, very important. And here I just show you the full picture of this dependence, how the frequency of magnons depends on the two-dimensional k vector in the film. See, it's quite complex two-dimensional dependence, but for us, this cut we have already discussed. You see, this is the minimum. This is the minimum at non-zero k vector. What I'd like to demonstrate here, it will be important for further consideration. There are two minima, of course, because the symmetry is k minus k is still, there are two minima, and that is important for our further. Now, can we get chemical potential equal to the minimum energy for free? Let us consider the thermodynamics. Usually, if we have equilibrium states, our magnons or magnetic system is in equilibrium with the lattice. It means there can be a particle exchange between magnetic system and the lattice. Magnons can be created, phonons can be annihilated, and that means due to this exchange of particles, the chemical potential of magnon gas is always zero at any temperature. This is main difference between magnon gas and the gas of atoms, because The number of atoms is independent of temperature, so they are this number. Therefore, the chemical potential at equilibrium in atomic gas depends just on the density. And as I have shown in my previous cartoons. In magnon gas, it's a system with a variable number of particles. Again, statistical physics third semester gives us the condition that chemical potential is equal to 0, but the minimum energy is not 0. And as we discussed a few minutes ago, we cannot make it 0 because then we have unstable ground state. So, no chance in equilibrium. And if we cool the system, it doesn't help. Chemical potential is equal to 0 at any temperature. How can we reach how can we reach BC? Well, we should increase chemical potentials for purpose. And the idea is we should introduce additional magnets by ourselves. If we bring the system a little bit away from the equilibrium and introduce additional magnets, the chemical potential goes up, and then we have a possibility to reach BAC. But now the question is, okay, we introduce additional magnets, but they try to go into the lattice because there is interaction. And this is the trick which we use in our experiment. We do it fast. So if we have possibility, if you have different time scales, and this is the reason why we use yttrium iron garnet, that exactly in this material, this is one of few materials where the spin-spin interaction time, or magnon-magnon interaction time, which determine you how magnons thermalize, how they go to their internal equilibrium, how fast. This time, this spin-spin, depends, of course, on many parameters, but it's in general much smaller than the lifetime of magnons, which determine how fast these magnons, which correspond to non-zero chemical potential, relax to the zero chemical potential. And if we see that we have at least a factor of 10, so we can think that if we inject different magnons, additional magnons, they thermalize and create us a quasi-equilibrium gas of magnons with non-zero chemical potential, and not just go immediately into the lattice. And experimentally, how we do that is rather simple. We have the film of yttrium iron garnet, and on the knees we have microwave resonator, and we put microwave frequency in this resonator, and there is so-called parametric excitation, where the microwave photon excites two magnons with the half energy, and in such a way we excite additional magnons in our system, and then we just let the system relax into the quasi-equilibrium. And if we do it fast, and we can get hope to get the quasi-equilibrium gas with a non-zero chemical potential. And using brilliant light scattering, in few slides I will present this technique. We control the gas of magnons. We measure how many magnons with the given energy we have, and that will be the main experimental technique I will be talking about. And to be sure that we will have this quasi-equilibrium, we of course should investigate magnon-magnon interaction and magnon-phonon interaction. I don't want to go into these details. I'd like to just to say that in this particular condition, under external influence, we can find a regime where yttrium iron garnet, magnon in yttrium garnet, first thermalize to a quasi-equilibrium, and then to the non-zero chemical potential, and then if we switch off our parametric pumping, it goes as a chemical potential to the zero. But if we keep keep pumping, we can get a quasi-equilibrium magnon gas. And this is our idea. Again, as I told you, to detect magnons, we use brilliant light scattering technique, not necessarily microfocus. In this particular case, it was macro brilliance. But the idea of brilliant light scattering is rather simple. The most simple consideration is a quantum. So if we have a laser beam, and we have a beam of photons with a given linear momentum and energy, and there is a non-zero probability that these photons excite a quasi-particle in the medium where it propagates. It might be phonons or or magnons, whatever it is. And just due to energy and momentum conservation law, it's change its angle linear momentum and also energy. And if we now analyze the spectrum of the scattered light, in addition to the unscattered light, intrinsic light, we will have brilliant satellites, and these brilliant satellites have information about these excited magnons. There should be also inverse process that this photon can absorb a magnon, and then its energy will increase. But the same is gives us information about existing magnons. On the classical, in the classical language, is rather also also can be explained if we have a quasi-particles which we have a wave, magnon, spin wave or sound wave. It's modulate the refraction index of the medium, and our light, which propagate in our system, just diffract on this wave of refraction index, and it goes in some direction. But since this wave of modulation refraction is dynamic, it's changed with the frequency of our wave. We have a phase modulation of this diffracted light, and the phase modulation brings us again in Fourier spectrum an additional frequency which differ from the intrinsic frequency by the frequency of the wave, whatever it is. But in general, brilliant light scattering is a very powerful technique because in signal is just directly proportional to the intensity of, in this particular case, magnetic oscillations, but it also can be phonons, and you can focus on your light, and you can get any possible resolutions. And this is very sensitive technique, because one can detect thermal magnetic fluctuation. And we will see how it goes without any additional excitation. And one can rather modest frequency resolution at the level of light, 10 to the 14th power. We have a frequency resolution 50 megahertz. Spatial resolution in free optics, it can be 200, 250 nanometers. In near field optics, again, for specialists, it can be as small as 50 nanometers. Temporal resolution, because it's light, it's very fast. You can get a temporal resolution rather small, about nanosecond. Again, you have wave vector resolution, or even phase resolution. So using this technique, you can get all possible information about your waves or quasi-particles. And as I said, usually people use this technique for to determine the dispersion of waves, sound or magnetic waves. So by fixing the scattering angle between incident and the scattered light, you fix the k vector, wave vector of the particle, which is allowed to participate in this process. And by measuring the frequency of the scattered light and difference between incident and the scattered light, you measure the density, the frequency of your quasi-particle. And you then change the scattering angle, you go to another k vector, you get another frequency, and so on and so forth. But we are interested in some thermodynamic properties of the magnon gas. So what we do, I don't want to go into details, just physically we averaged or integrate this signal over quite large area of k vector. And instead of getting narrow peaks, we have a broad peak which is determined by the product of the population function, number of particles populating a given state with the given frequency or given energy, multiplied by the density of states. So it means if we know the density of states, and the density of states can be calculated from the spectrum, known spectrum, from the BLS spectrum, we can obtain these as population functions which we are interested in. Well, now we are going to the experimental results. So what we see here the brilliant spectrum, which correspond to the magnons. And what we do, we start to pumping at time equals 0, and we measure spectrum at a given time. So of course, this is stroboscopic technique. We repeat the measurements many times, millions of times. And using these stroboscopic measurements, we can get this distribution. And what happens? Well, as soon as our microwave power is switched on, we pump more and more magnons in our system, and they thermalize. And after some time delay, we measure with brilliant scattering what is their distribution. And you see here different curves, and by corresponding to the different time delays, it means corresponding to the different number of additionally injected magnets. And just by fitting these curves, since we know the density of states, we can get the population function as a function of omega, and knowing the Bose-Einstein statistics formula, we can fit this with the chemical potential. And this fit parameter chemical potential is shown here. And what we see, for this particular experimental condition, we have more magnons we excite, higher is chemical potential, but the minimum energy which we have corresponds to the 2.1 gigahertz, and we see that in this particular case, our chemical potential saturates just below this value, and we cannot reach any Bose-Einstein condensation. And this theoretical curve will give us distribution which we would have if the chemical potential will be exactly equal to 2.1, and that will be a transition point.
That doesn't change as you go to higher and higher tau.
Sorry?
That doesn't change, that curve, as you go to higher and higher taus.
Higher what?
Time delays.
Yeah, well, it's saturated. You see 1.7, 1.10, 2.4, 2.7, it's just saturated. I will show you the temperature, the time dependence of the chemical potential. But yeah, here. This is curve for this particular power. And you see, well, I choose this power just to show that we asymptotically go to this critical value, but we're still below. But if we increase the power just a little bit, instead of 4 watt, we have 6 watt, very fast we are in the critical regime. And what happens here, that was the curve which on the previous slide, which corresponds to the critical chemical potential. And you see that it's very fast. We reach this critical value. And then after we start to bring more and more magnons, what happens? This part of the distribution is not changing at all. You see, 300, 400, 500 nanosecond, it means more and more particles. Nothing happens. But close to the minimum, we see a huge growth of the population. This is exactly what Einstein predicted. We bring more and more particles, and since the Bose-Einstein distribution with non-zero, with high energies is already saturated, we cannot bring more particles in this system. All additional particles comes to the minimum energy. Of course, you see that this peak is not delta peaks, but okay, we will see that this frequency distribution is just instrumental. I will show you some results with a better frequency resolution, and we will see that. What is important to see here is that beginning with some critical value of number of particles in this particular experiment, it means 300 nanosecond time delay, all particles, all additional particles we bring into the system after some short thermalization find themselves here. Nothing happens here. Again, so this is, again, I show it as here, the different compare with these 4 and 6, 4 and 6 watts. We see here clear creation of the condensate because the particles are in the minimum energy. So we can, in our optical technique is we can increase the resolution for the price of time measurements. Therefore, we will not we make just very few measurements with ultimate resolution. And what is shown here, it is difference between experimentally measured technique and the experimental curve and the curve which we calculate or which we obtain for the critical value of chemical potential. Strictly speaking, we subtract from this measured curve, from measured values, this critical curve. And with normal resolution, we get this blue curve. But if we make the resolution, frequency resolution better, we see that this peak becomes narrow. And in this particular experiment, the line width is 30 megahertz and corresponds to 1.5 millikelvin. It's about 5 order of magnitude of the temperature we are working with. And this is, for us, a clear indication that we create condensate. I will show you experiments with even better resolution, and even I will show you experiment where we measure the interference of two condensate. But already these results, I think it's amazing. You have a system at room temperature, and then you pump magnons in some, it's completely different frequency. So what we pump, the magnons, they are somewhere here. And after some thermalization, this gas built a distribution with a line width of 1.5 millikelvin, although the total temperature of our system is a room temperature. It's really amazing. And wave vector. Well, it corresponds to the minimum of spectrum. I will show you. This is This is 0.3 10 to minus 5 fifths inverse centimeter. So the wavelength is about half a micrometer. Okay, So it's really amazing, but we know that even that width is instrumental. And to measure, well, this is exactly what people observe for atoms. The narrow peaks, and they also have a finite width, although they claim that it's coherent state, and well, in experimental technique, we never get delta function. But we would like to increase and to measure intrinsic width of our condensate. Again, in theory, the line width of the condensate is 0, but we would like to see what is the real. Yeah?
So I was wondering the real space physical picture of the condensation. So condensation in the finite wavelength, is it corresponding to a spatial modulation of textures in the thin film?
Well, it's not a texture in the sense of dynamics. You can, if you recall my first slide, or one of the first slides with the moving spin waves, as a matter of fact, this is already shows you how condensate looks like. Again, it corresponds to a given frequency and a given k vector. Oops. This is exactly, you see, all spins, or most of the spins, precess in phase, but the phase depends on the position, and you see it corresponds to some non-zero k vector, but it's still coherent.
So there will not be a standing wave. So it's propagating.
Okay, wait, there will be standing wave, but the standing wave will be as a result of interference of two condensate. Okay, now this is just for one condensate, it's a moving wave because it corresponds to non-zero k vector. But as you are correct, since we have degeneracy, we have plus and minus k, we will see that k as the standing wave. But for that, instead of measuring with k vector resolution, we have to measure with a real space resolution. Then we will see.
So if there's some DME correction, then the forward propagating and the backward wave will no longer form a standing wave, right?
Yeah, then it will be. But I will show you that in our case, the symmetry is there, so we have a standing wave. And that will be, for me, ultimate confirmation that we have coherent state. Okay, let's go again. I will probably skip these technical details, just say that we developed heterodyne spectroscopy, which gives us possibility to perform spectroscopy with a visible light with the frequency resolution about 100 hertz. So we can measure the frequency of light with the 10 to 14th with the accuracy of 100 hertz. But I don't want to go into details, but 200 hertz. But if we apply this technique and measure the line width of the condensate, we see intrinsic line width of the condensate in the frequency, and it's about 800 kilohertz. Again, the frequency of magnons, the frequency of condensate is 2 gigahertz, and the line width is 800 kilohertz. So it's a very high degree of coherence. Of course, it's finite, contrary to prediction of theoretician or simple description of orientation, but it's still huge degree of coherence. What is also interesting, if we measure these intrinsic line widths and intrinsic profile, we see that it's not symmetrical. And again, it's symmetrical. It's the shoulder at higher frequencies is broader than in low frequency. And that means that in addition to the just a ground state of condensate, we have some kind of excitation on the top of condensate. And the standard excitation of a condensate is the second sound. And we have observed the second sound in gas, but I don't want to go into this work today. Sorry?
What limits the limit?
Quasi-equilibrium nature, because we are not in equilibrium. So it means we have continuous flow of the condensate. We have continuously non-condensate magnets. We bring these magnets. They go to the condensate, and then it will be a little bit shifted, modulate the phase. And then we have a flow somehow, for some rate, magnons disappeared, they die out, but there is another. This is one mechanism. We don't know, as I said, but what another mechanism is that it might be some interaction within the excitation. But to be honest, I think that it's just to non-equilibrium, well, quasi-equilibrium nature of this condensate. I think so. And well, on the other hand, in real situation, in experiment, you always have non-zero line widths, and due to interaction, whatever it is. Sorry?
The second sound that you mentioned, the asymmetry in the peak?
No, because you have the second sound has some dispersion. We know that it's linear, and since we're not excited by themselves, so there is all possible wavelengths. Therefore, it gives your shoulder some wave vectors of broad interval of wave vectors and broad interval of frequency. So I think this is. Okay, another? Yeah.
What's the width of the magnons that you're pumping in K-space?
In K-space, I will show you. We bring them in. It's a whole contour in K-space. Well, I will probably skip here because this is a lot of, we investigated the process of thermalization, how it happens, what is going on. But I think this is for today, it's not so interesting. Probably here we investigate, as you suggested, we have measured with the K resolution. What you seen before, it was integrated over the K. We are interested only on the question, how many magnons with the given energy we have. Because we knew that the minimum energy has only two points, everything else was for us not interesting. But we also wanted to make resolution measurements with the K resolution. And this is the experimental technique, well, is the same. Well, it's not, again, not so interesting. This is the results. This is what I promise you to show. This is a snapshot. I will show you. Oh, you see how it happens with the time. But before you look at this, from my point of view, marvelous picture, movie, let us make shot by shot. So we have parametric excitation. So it means we create all possible magnons with the frequency which is half of the frequency of our microwave. Since you have seen that the dispersion relation of a magnons is quite complex, it's not is anisotropic. So we just cut this two-dimensional sheet by some frequency. Therefore, we have a contour of magnons with the different K vectors. And what you see here, well, our experiment was rather simple. We switch on the microwave pulse and then switch off. So we create some kind of contour of magnons and then just wait until they relax. You can also get basic condensation on this way, but then this condensate disappear very fast. And what you see here, that is just part of this contour, and the rest is beyond our measurement technique. But then we wait some time, and we see how this magnons goes down in the frequency, and they also concentrate closer and closer to this minima. And you see, after some time, they already make a real circle or real ring. Then they go closer and closer, and finally they all concentrated in the point, which it's not I put it here just because I have this picture. I calculated that, I put this number because I know it's from the spectrum. And now if we put all these snapshots into the movie, you see how it works in time. So this is in time, and the typical, well, the entire process takes place, as you see, in several hundred nanoseconds, and you see how these magnons excited magnons, non-coherent magnons, yeah, because they have the same frequency, but this frequency has nothing to do with the frequency of the minimum state. But they have different k vectors, but after some thermalization time, they all are collected in in one point in the k space with the sum, of course, resolution. Now, this is back to your question, standing wave. Again, we have seen this picture already. So it means we have two minima. Well, I probably will not be able to go to the spin Hall effect, but sorry, I had already questions and I have to answer them. So we have two minima, and it means we have two condensate which have opposite k vector. And if this rather simple example gives you, for example, standing wave of light or any, it should give us this, if we have a wave, the same k vector but opposite in opposite direction, we should observe the standing wave of total density. Well, how can we do that? Well, instead of, and it happens only if these two Bose-condensate not only coherent within itself, if they are also phase locked to each other. Otherwise, you will have some beating in the standing wave, and the standing wave will be washed out, and then we will not observe any standing wave, although each condensate can be coherent. But if we observe a standing wave, we have it that each condensate is coherent, and they are phase locked. Well, what is the experiment? Instead of making k-resolved measurements, now we make space-resolved measurements. We focused our beam very tiny, and then the scan. And again, we are measuring the intensity of this peak, and what we observe here. You see that there is a standing wave of density, and again, this sinusoid which I put here, it's not a fit. Since I know k vector, I just plot here the double k vector, and you see it fits perfectly. Moreover, in addition to this standing wave of density, you see here bifurcation. You see here how of three red lines we have two, and in cooperation with theoretician, we were able to show that this bifurcation corresponds to quantized vortices. Again, let me remind you, what you see here, it's a dynamic picture. It's the density of precession, coherent precession. All spins are precessing with a given frequency, and what we see here is the density, or is the square of amplitude of this precession. Nevertheless, in some places, and we know that these places are defect in the lattice, we have vortices, And, well, first of all, it's the same. And based on this equation, which is very similar to Gross-Pitaevsky equation, which described the creation of condensate in atomic, we were able to show that this structure corresponds to the quantized vortices in these condensates. Very similar to that.
I'm sorry. So, when the standing waves work, the local oscillation is still circularly polarized.
No, it's not circular. It's elliptically from the beginning, because we have film, and in a film from the beginning, even for one condensate, it's elliptically because you have anisotropy, out of plane anisotropy. It's elliptically. But strictly speaking, we are not measuring the polarization because our signal is something averaged of the Bose component. So what we can say that just the total amplitude or the sum of squared, something like that. So we cannot say. But this is very similar to the bifurcation people see in atomic condensate. Okay, so you are the boss. Will you give me 5 minutes or 10 minutes?
So we have to be out of the room in less than 15 minutes.
So if you have questions to this part of the talk, I will be happy to answer. Otherwise, I tell you a story how we tried, but without, well, real success, to get Bose-Einstein condensation in metallic system using the spin current. Well, it's up to you. Go ahead. Okay, so we know that electron has a charge and spin. And therefore, when we have a coupled wire, we have electric current, but no spin current, because 50% of electrons go spin up and 50% of electrons have spin down. So if you would have a wire, not out of copper, but out of iron, you will have spin polarized electric current. And the spin polarized electric current is well known since already 20 years, can be used to create oscillations in magnetic system. So you inject spins in your system. If the polarization of your injected electrons is proper chosen, you make your system unstable, it starts to rotate. Or in some cases, it's a switch, but it starts to rotate. We use not spin polarized electric current, but we use pure spin current. Again, pure spin current corresponds to the situation where we have spins, electrons with spin up and spin down moving in opposite direction. And the mechanism for that is called, well, it's microscopic mechanism, spin orbital coupling, but macroscopical it's called spin Hall effect. And if I have a system where I have film with a strong spin orbital coupling, and on the top I have ferromagnet, is it possible to switch on? No. So if I have such a system, if I have a scattering angle, believe me that spins in one direction will be scattered to the ferromagnet. Electrons with a spin in opposite direction will be scattered out of ferromagnet. It means they go in opposite direction. It means we have a spin current in that direction, so we inject really spins into the ferromagnet, and everything if everything is made properly, we create precession in our ferromagnet. In other words, we inject magnons. So the same story. We inject magnons by another technique, and we hope that we will be able to observe Bose-Einstein condensation. But in the beginning, we'd like to see whether we will be able to at least to get a guess of magnons and quasi-equilibrium, and to measure whether we have non-zero chemical potential. And the experimental, in our case, is the following. We have a platinum structure, you see underneath of permalloy, and we put electric current into platinum. Its platinum creates a spin current in vertical direction, which injected in permalloy, and then we can excite magnons. Here is experiment, for example. Oops, here we have our brilliant light scattering peak. It's zero current. If we increase the current, we have a huge number of excited magnons. And if the current is opposite direction, we suppress. We just absorb magnets. And again, the same story. We have rather broad peak, and we know the density of states. And just based on this peak, we can determine temperature and the chemical potential. Just to make a calibration of our system, we just make a direct heating, and we were measuring this peak at different temperatures. And if you make a simple arithmetic, you see that the ratio of the population function is just give you by ratio of the brilliant light scattering functions. So the density of states is just canceled. And if we just change the temperature, with this ratio is just a constant, independent on the frequency. And in effect, in this calibration experiment, you see that the ratio is a constant, and based on this value of this constant, we can determine from this peak the temperature, and it nicely corresponds to the value we get from our thermometer. Nice, everything is perfect. Now, we introduce a spin current, and therefore we should expect the non-zero chemical potential. But now, if the chemical potential is not zero, the ratio which gives us this is frequency dependent. Again, we make first negative currents. It means we absorb magnets of our system. And what is interesting, we again obtain ratio which is frequency independent. But less than 1, it means that we cool the system. Nothing happens with the chemical potential. It doesn't go into negative value, but the temperature goes down. So it's amazing for me. We have a system which will just let on the desk, and at room temperature, we put electric current, and the temperature goes to almost 200 K in the magnetic system, the temperature of the magnetic system. Now we change the current, and we inject magnons, and what you see, what happens, this is zero, again, zero current, and this is non-zero current. And if we now make a ratio, you see this is strongly frequency dependent, exactly as we expect from Bose-Einstein statistic from non-zero chemical potential, and we can determine chemical potential from this measurement. Now, the same game, we want to make this chemical potential equal to the minimum energy. So we increase the current and measure the chemical potential, and simultaneously we measure the minimum energy. And what happens? In the beginning, so far so good. It goes very fast to the minimum energy, but as soon as you have it close, something happens, and we believe we know what happens. In this metallic system, the magnon-magnon interaction is such that this interaction causes very effective, very efficient flow of angular momentum into the lattice, unfortunately. So the interaction does not conserve the number of particles, and therefore, if we have increasing chemical potential, it means the number of particles at low frequencies increase dramatically. Remind you, this is logarithmic scale, so here we have increase by order of magnitudes, and this interaction breaks us the possibility to go here, and we observe gas with non-zero chemical potential, but unfortunately we are not able here to observe Bose-Einstein condensation, and we are working now to try to get rid of this unpleasant interaction by constructing different materials, and we hope that we will be able to observe similar effect in metallic films. Yeah.
Can you try this? Can you do this in E?
Sorry?
Can you do this in E with platinum?
Yes, we can. The problem is if you, yeah, I understand. The problem is the experiments with EEC I gave you before. It was with very thick film of EEC. It was 5 micrometers. Since spin current injection in the surface effect, if we will put platinum on EEC on such a thickness, nothing happens because it's. But if we make EEC thin, and we made these experiments, and we create already non-oscillators and everything. But then these thin EEC films have large damping. And again, we are not able to go to the critical regime. We have very similar picture as here. Okay, I'm done.
Ferromagnetic metal, I guess I would assume the magnon's primary decay mechanism is in the stoner excitation. Is that something you guys have thought of?
Not necessarily. The main reason, the main difference between EEC and permalloy is that the magnetization of permalloy is 10 times larger than in EEC, of 5 or 6. And that means the dipole-dipole interaction is much more stronger than in EEC. As we discussed today, the dipole-dipole interaction coupled spin system with the lattice. Therefore, in permalloy, this coupling is much more efficient than in EEC. It has nothing to do with defects, and this is intrinsic. So? Well, the electronic excitation, it doesn't bring the angular momentum. We are talking about angular momentum. I don't know. Well, I don't know, but for me, probably you're right. I don't know, but we believe that at these frequencies, what we have, it's not a stoner excitation; it's just their direct coupling to the lattice. Well, but we can. What it might be. Well, but to be honest, we don't know exactly why, but we see that when we have a large number of magnets, we pump additional angular momentum, but it's disappear. But we know that it's the only place where it can disappear. This is a lattice. Whatever is the mechanism of that.
Yeah, I have a question about the dispersion. So both in EEG and in permalloy, it's all rise up. It's
Yeah.
low key number. Design I notice you use nanowire. So do you intentionally design the shape and socket to get that, or for the whole film you will get that dispersion?
Very good question. For very thick film, you have such a pronounced minimum because the speed how this dipole interaction goes down is proportional to the thickness of the film. In the thin films, this minimum is not very pronounced, and therefore the spectrum is rather flat. And in thin films, where we will take, if you just take just film, we will not be able to determine chemical potential because our peak will be narrow, and we don't have this frequency dependence. We design our system for purpose to have a broad peak, even for rather thin film, just to have a possibility to distinguish between different states with a different energy, to have a possibility to distinguish between changing of temperature and changing of chemical potential. So it's occasional. In one case, we have thick films, and then we get these broad peak for free. In thin films, we would have for free just a narrow peak, but we make a special design to have a broad peak and to be able to create, to analyze this peak in broad frequency regime.